Okay, I am going with the questions in this. So let's do the question for strain energy. I am giving you a question. Suppose this is cantilever. Now this is a cantilever beam and a P load is applied. Okay, this is your length L. Now I am asking you to find the energy stored in the cantilever. Then apply Clean's theorem like del U by del P is equal to delta. Obtain the deflection at point C. Then apply del U by del M at C to obtain the theta. So what would be the expected result? Expected result will be PL cube by 3 EI, and here the expected result is PL square by 2 EI. So taking the energy, so it is bending, so let's take strain energy of bending. Okay, that is integral m square dx upon 2 EI. So here you can write it like integral. First of all, what is the m? Suppose I take any section x. Okay, so you take. Okay, now I am going to integrate it with minus px whole is dx upon 2 EI. So this equation will become upon 2 EI. I will take out outside. It is x square dx and limit is 0 to L. So the strain energy would be E square upon 2 EI, and it is x cube by 3 from 0 to L. So it will be P square upon 2 EI into L. It is L cube by 3. That is equal to P square L cube by 6 EI. So this is the strain energy stored in the cantilever for this P loading. Now I am going to apply the Castellano's theorem, that is del, suppose I represent it by U. So del U by del P, I will differentiate it. So del by del P of P square L cube upon 6 EI, differentiated the L cube upon 6 EI, that is equal to PL cube by 3 EI. I hope everyone getting this. Is it okay? Is it okay? Okay, now I am going with finding the slope. So you for finding the slope with respect to the moment. So first of all, what is the we are taking the moment. So what is the equation, that is m square dx upon. Now if we differentiate it with respect to moment, what would be the value? It is m 2m dx upon 2 EI. So it is integral m dx upon. You see that your m is equal to minus px. So I am going to write it like this. Integral 0 to L minus px dx upon 2 EI. P square, P square, P into 0 to L upon EI. So your value will be PL square upon 2 EI. Your negative sign would be that of slope. It doesn't matter because you are getting the same result for the slope as we obtained for the. I hope everyone are getting this. So what I am going to do with the next problem is, suppose the thing I am going to do is, now easy because you have direct formula for that and you can easily obtain. So there is no need to apply the strain energy. Now suppose a L-shaped member. Okay, this is called A, this is called B, and this is called C, and you apply a load suppose P here, and this is your length L, and this is your length h. So now you need to add, or you can see delta at C, deflection at point C. How you need to obtain? Then we are going to use that same principle, Castigliano's theorem. So divide the structure in two parts, BC and AB. So as strain energy in BC plus strain energy in AB. Because as you can see, both are same material, so I take E and I as their property. Now you can say, okay sir, we can take this as a cantilever, this portion, but what you will say about this? Because it will deform like this. It will deform. So what I should do is, I will obtain strain energy for BC. That is integral m square dx upon 2ei. That is equal to, if you take it as p into x, so integral dx whole square minus px, it would be L cube upon 3ei. Is it okay? This is the BC. Now for AB, let us say what is the load acting on AB. So this is your AB and this is your BC. So suppose this is your AB, this is your BC. I separated out to obtain the free body diagram. Now P load is acting here. Now if I want to transfer this load here at this point, I need to make a couple, that is P into L. That is P into L. How I am getting this? I already told you. Suppose this is your load and it is acting here, and if you want to shift here, so apply a load opposite in this direction so that no effect will be there. Now this load and this load with this load form a couple that will act in this direction. So as we can see, now at V point we have a load this and a couple this M, that is P into L. I hope everyone is getting what I am trying to say. Now, so for strain energy at AB, so this was your structure of AB. You have a load P and a deflection M. So we can assume that the load P is much smaller than the deflection bending stress. Hence, we only define with the bending only. But you can also go with strain with the axial compression, but it will not affect much. So strain energy at AB is equal to integral m square dx upon 2ei. So here m is constant, that is P into L, so it will be outside P square L square upon 2ei, and in dx that will be x from 0 to h. Here the value is h, height is h. So you are getting the energy like P square L square h upon 2ei. I hope everyone is getting. Now your total strain energy will be would be P square L cube upon 3ei plus P square L square h upon 2ei. This value, wait a sec. Sorry, here in which expression you are trying to say? Okay. Actually, I am not getting your voice. Please write in chat box. Can you write that? Oh no. Here you are trying to say, na? Okay, okay, I got it. I got it. Okay, you are trying to say at this point 6 ei. Yes, here. This part you are trying to say, na? Hello. Yeah, so it is 6 ei. Sorry, it is 6 ei. Yeah. So this would be the expression Now if I want to obtain the what is the vertical deflection at, because the load is acting in this direction, so what is the vertical load acting in what is the delta is, that is the deflection, vertical deflection at the point. So you need to differentiate it. Suppose this is u, you need to differentiate it with respect to p. Okay, now it will be 2p L cube upon 6 EI plus okay, someone messaged me. Hello, the value is 2p L square h upon 2 EI. So you are getting the value as plus p L square h upon 2 EI. Sorry, EI. This is your deflection at point C in vertical direction. Now I am going to ask it in another term. No, yeah, I hope everyone gets it. Is it okay to you? Hello. Okay. Now I am going to make a little change. Okay. Now the change is, for the same question that was above, this is length L. Okay, and this is supported. This is your load P. Okay, and the properties are EI. I want to ask you. Yes, this. Please, someone is unmuted. Please mute yourself. Okay. I just obtained the deflection at suppose this is A, this is B, this is C. So I just obtained vertical deflection at point C. Vertical deflection. This rod is bending like this. Suppose this is bending like this. Okay. Now I want to obtain what is the delta C in horizontal direction. Delta CH. Now you cannot derive it with energy method, double integration method. You have to use the energy method only to solve this question. Now this leads to another concept of the theorem. So I am going to explain it. So I am going to put another load Q. Why I am putting, I will tell you. I will tell you in the later section why I am putting it. Suppose I am putting a load Q in the direction in which I want to find the deflection. So now obtain the total energy in the body. So with the also take the load Q with yourself. So first of all, strain energy at point BC. What it will be? Integral m square dx upon 2 EI. That is for P, and we neglect the value of the axial load. Axial means the tensile load on the normal load that is coming. We are not going to take. We are going to take only bending stress, because in comparison to bending, axial is very small. Okay. Now integral, what will be the value? Px whole square dx upon 2 EI L cube upon 6 EI. This is your one expression. Now for Q, if you see that this is value P, this is value Q, and here you have a couple that is that you say it is PL. Okay. Now strain energy at AB. So I am drawing AB in a separate position. So this is your AB. This is your load P that I am not going to take, because actual strain energy is very small in compared to bending strain energy. I am going to take the couple PL, and I am going to take this load Q, because this load will form a bending in this direction for the beam. So strain energy AB is equal to integral m square dx upon 2 EI because of the couple that is PL. Okay, plus integral m square dx. Now if you solve this, here m is constant, that is PL, it will come outside p square L square and into h upon 2EI. This would be the expression, plus here the q value is also trying to rotate it in this way, so a couple will act, that is q into x dx upon 2EI integral 0 to h. Now this expression would lead to, only this expression would lead to q square, sorry, this is q square x h cube upon 6EI. Now total strain energy in the body is, you can see that what is the total strain energy in the body. From the two expressions we can see strain energy total is equal to P square L cube upon 6EI plus P square L square H upon 2EI plus Q. Okay, now what I have to do is, you have to differentiate with respect to Q, because that in that direction only Q load is acting. That's why I had taken a Q load, because we have to take that load. What I said earlier, you can form the deformation in the direction of P load. That gives a deformation in direction of P load. So there in horizontal direction there is no load. So I applied a Q load and I am going to differentiate now with the respect of Q. So now your value with the respect differentiating with respect to Q is 0. Okay, in this differentiating, this value is also 0, and here I am getting 2Q, and after that I need to put at Q is equal to 0. Why? Because there was no load earlier, so I assume the Q load, but I need to put in the strain energy as Q is equal to 0. Okay, then when I put at Q is equal to 0, I obtain that at point P, at point C, I obtain that there is no horizontal deformation. But in some other cases there may be a horizontal deformation. So what I want to say is, in this theorem, if you are obtaining the load in that direction where the P is applied, it cannot be, you cannot apply this formula in uniformly distributed load. So how we obtain in uniformly distributed load, I am going to explain that. You have a uniformly distributed load. Okay, in let me take cantilever beam, and you need to find a deflection at point C. At point C, but here there is no particular load that will for that to differentiate and you can obtain at that point. So what we assume is the same thing. Assume a load P in this direction, that is although 0, but assume it and obtain the strain energy. So what will be the strain energy because of this load? So first of all, what is the moment m at distance x? Moment m at distance x is P into x plus that is, suppose this is W, width per unit length, and whole length is L. So that will be W into x by 2. That is Px at this point, at any distance x. Now what is the strain energy of the body? The strain energy of the body is m squared dx upon 2EI. Now when you plus Wx square by 2 whole square dx upon 2EI. So if you just first of all square the inner term, that is P square x square plus omega square x to the power 4 by 4 plus 2 times the expression plus omega square 4 by 4 plus 2 times P omega x cube by 2 dx upon 2EI. I am taking 1 upon 2i outside, I will cancel it later. P square x cube upon 3 plus W square x to the power 5 by 20 plus 2 and 2 would cancel, Pw x to the power 4 by 4, and that would be 0 to L. So I am going to put it like this. It would be I am putting x equal to L, so the value would be P square L cube upon 3 plus W square x to the power 5 by L to the power 5 by 20 plus Pw x L to the power 4 by 4. So now what I am going to get is differentiate it with respect to P, because we applied the load P, so differentiate it with respect to P. That would be 1 upon 2 EI. Okay, if I differentiate this, it will be 2P L cube upon 3 plus this would be 0, and this would be omega 4 omega L cube upon 4. So and now put P is equal to 0. So I am getting there is something that is wrong. Okay, I will explain this part to you after in next, because something is getting wrong. Okay, I will just go with the strain energy question. So because this 4 need not to come in. Oh, sorry, yeah, it is right. Oh, I got it. What the wrong, nothing is wrong here. So now I am going to put P is equal to 0, then it would be 1 upon 2I. If I put P is equal to 0, this term would be 0, then it will be W L for 4 upon 4, and that would be W L for at end point, and that is the expression that we used to get when we apply the double integration method. So I hope this is clear to you. Hello. Any problem? Okay. And so what are the limitation of this theorem? I am going to write it. So first of all, you cannot apply in the condition other than point load. If there were no point load, you cannot apply. Hence, if there is no point load, assume the point load, then substitute the value, differentiate with respect to that load, and put the value equal to 0. You can get the deflection. Okay, this is the first condition of this theorem. So if there is no force, assume the force in this direction. That differentiate with respect to P, find the strain energy, differentiate with respect to that load, and put that load is equal to 0. So this is one of the strain energy, and this is very important concept in deriving any problem. Just like this question here, that what I get in this part is you can obtain that. Okay. Now I'm going to give you a few questions. So suppose okay, I think that thing is enough, because I only left with 1 hour, so I go with thin cylinder also. So solve the strain energy problem. It is easy for you. Only use the formula that I that is equal to integral T square dx upon 2Cj, that is equal to tau square dx upon 4C, and that is equal to half into stress into strain. So apply these formulas to obtain the relation, obtain the strain energy in a body. So I am giving you a work, find deflection of uniformly distributed load in simply supported beam with this formula. Okay, simply supported load with this formula, that is with this theorem, that means with this theorem. Okay, this is the if you can do that, means you are is it okay? Okay, I am going with the thin cylinder part. So I hope everyone sees the cylinder. It is for the storage and for supply also. So designing of thin cylinder is like dealing with, because whenever certain fluid is stored in the body, suppose you have a cylinder and certain fluid is stored in the body at a high pressure, then you can assume that this outer surface would like to come out, but the material strength is resisting not to come out. Hence, there would be a stress generated in the walls, and that we need to analyze and hence design. Hence, design of cylinder is how much would be the dimension, how much would be the diameter, how much would be the thickness to take that load. I hope you everyone has seen the boiler. So in boiler, they have a chamber like this only, okay, and inside pressure is in megapascal. Now we need to design the thickness of the wall. We need to design the diameter of the walls so that it will not burst out. So that design is came from the in your gate course only thin cylinders are there. So we are going to design the thin cylinders. So what is the thin cylinders? Thin cylinders are of when thickness of cylinders 10% of inner dia. So this is the definition. When thickness of cylinder is 10% is less than 10% of inner dia. Now, what are the types of stresses that arise in the cylinders? So basically, I just draw because in 3D I cannot make you visible. So that's why I put it from the the part will split like this, and there is a breakage like this. So at this point, there is a load is acting like this, or you can say this is there is a material that is in stress, because these two parts are attached with a bond. Okay, now when certain fluid is filled with a pressure, they will try to come out, but the bond the strength of the material does not allow to do this. Hence, what are the stresses originates because of the internal pressure is in thin cylinders at this location is called circumferential stress, circumferential stress or hoop stress. So the body will try to come out along the diameter, means you can say that in one of the axis of diameter, means this one try to split into half. Okay, so here you can see that this is the stress that is that hold the two material in between. Now there is another case. This is the same case, circumferential stress. Now here the case that if this body is break like this, hence that this is called, suppose this is the one part of the body, this is your second part of the body, and it is breaking like this. So the material, suppose I draw it like here, and also suppose this is your two part and they are attached. Okay, this is where they are attached. Hence along this axis they can break, and this is called the longitudinal stress. The stress that originates in the body along the longitudinal direction is called longitudinal stress. So this so what I want to say is in figure. So suppose this is your cylinder. Now if you see that circumferential stress, we try to split the two part, and if it doesn't split, it will go on increase the diameter, because if something is happening, okay, like this, and it will try to increase the diameter. Suppose internally pressurized fluid is filled in the cylinder, and if it will try to increase the diameter, that is resisted by this circumferential stress. Hence we can say that circumferential stress circumferential stress is related to change in diameter, is related to change in diameter. And giving that this part, you can say the stress is along the length direction. Hence this will related to increase in length. Therefore longitudinal stress related to change in length, change in length. So that is the one case. Now suppose the expression would be, I am not going to derive that, but it is easy. Sigma circumferential is equal to PD by 2T, and how you get that, let me explain from this figure. Okay, I am going to explain how we are going to derive this. Is acting along this direction. So what would be the force along the circumference? So if you just multiply sigma c with, this is your length, and this is your thickness. So length into t, first of all, here also you can see length into t. So there are two times length into t. Okay, you can see this happening in the body, and that is equal to p into, you can say this is your length d and your length l. So the projected area of your cylinder is d into l. So you are getting sigma c is equal to, you cut out l, it is pd by 2t. Now in longitudinal stress, we have an area like this, and in this surface they are projecting outside. So the sigma l into pi by 4, or I can say not pi by 4, it would be pi d into t, that is the area of this plane. If you take pi d, this is your inner perimeter, into thickness, that would be the area. This is equal to p into pi by 4 d square. That means if your end is closed here, suppose if your end is closed here, so and your P is force is acting inside the pressure. So what would be the force that is acting along the direction? That would be P into pi by 4 d square. Hence they need to be equal along the length. So if you solve this, your sigma L would be P d by 4t. So this is your longitudinal stress, this is your circumferential stress, and I assume everyone got with it. So is it okay? I am audible? Hello. I am going with the strain part. Now, first of all, when there is fluid filled inside the body, when a fluid is filled inside a body, so there originates strain and stress. So I discussed about the longitudinal and circumferential stress. Longitudinal and now I am going to ask you what would be the strain in d direction, that is in the diameter direction, and strain in the length direction, that is delta d by d, and this is delta l by l. So the circumferential stress which try to increase the diameter, okay, then it would be pd by 2t e. this is your strain, this is your stress divided by epsilon, divided by E, that would be strain. But this longitudinal stress is along the length direction, and it will also try to reduce the diameter. How? Because of the Poisson's ratio plus mu times PD by 4T E. And here also the length in length direction, the longitudinal stress will directly contribute, but your circumferential stress will try to do with the Poisson's ratio. So that would be the elongation along the diameter and elongation along the length. So if anyone has any doubt in it, I am going to simplify it. So I am writing epsilon d, that is change in diameter with the original diameter, that is PD upon 4TE. Okay, this is 2 minus mu, and your epsilon L is delta L upon L, that is PD upon 4TE 1 minus 2 mu. This is I hope everyone is clear with it. Now I am going to use this and form the volumetric strain of the cylinder. So if I write volume of the cylinder, V is equal to pi r square h, or pi by 4 d square h. I hope everyone knows this. Now I am going to take log both sides, log of pi by 4 plus 2 times log of d plus log of h, or L. In general notation it is L. Now I am going to differentiate it. Now what it will be? 1 by V dV is equal to, this is 0 because this is a constant term, to 1 by d delta d plus 1 by L delta L. So if I write it like this, then it will be delta V by V is equal to 2 times delta d by d plus delta L by L. Is it okay? So diametric strain plus longitudinal strain, and if I put the value, what it will be? PD by 4T into 2 minus mu, that will be the diametrical strain, plus PD by 4TE into 1 minus 2 mu. And if I take it common, PD by 4TE, so it is 4 minus 2 mu plus 1 minus 2 mu, that is equal to PD upon 4TE 5 minus 4 mu. So this is the volumetric strain in the cylinder when the fluid is internally filled with a fluid with pressure P. So this is your fluid pressure. This is your diameter, inner diameter. This is your thickness. This is your Young modulus. This mu is the Poisson's ratio. So I hope everyone is clear with it. So this is your volumetric strain in the pipe. So suppose there is also one thing. What is the ratio of hoop strain to longitudinal strain? Hoop strain to longitudinal strain. Hoop strain is also, we can call it delta d by d because it is in the direction of hoop stress or circumferential stress, and it is delta L by L. This value is PD by 4TE 2 minus mu, and this value is PD by 4TE 1 minus 2 mu. So I will cancel this and it will be 2 minus mu upon 1 minus 2 mu. This is your ratio. Okay. So this is a hoop strain and this is the ratio for both the things. Now few questions with the thin cylinders and this. Anyone have any doubt? They can ask me. I'm going with the question. Okay, I'm going with the question. Now let me go give you a question. It is given a closed thin circular of diameter 40 200 mm and wall thickness 10 mm is filled with a gas of pressure 10 megapascal. Question is find maximum shear stress. Maximum shear stress developed in the wall. So I am giving you 1 minute time. Please think about it. Okay. So first of all, in this question, what would be the hoop stress or circumferential stress? PD by 2T. That would be equal to 10 into what is the diameter? 200 megapascal. Okay. Now what would be the longitudinal strain, or this would be PD by 40, that is equal to 50 megapascal. Now they asked what is the maximum shear stress developed in the wall. So I want to say maximum shear stress. So maximum shear stress would be first of all, in earlier case when we used to draw this rectangle, we considered it at 2 dimensions. But let me but cylinder is in 3 dimensions. So there need to now suppose this is your Mohr circle. I am going to draw the Mohr circle, sigma versus T. Now you have one sigma 3 that is 0, 0, it is sigma 3. Your another longitudinal is 50, so I am writing it like 50, sigma 2, 0, that is 50, 0, and another is 100, 0. Now you can draw three more circles from it. And what are they? First of all, in between, so this is your sigma 1. So first of all, in between this and this, sigma 1 and sigma 3. Second is sigma 1 and sigma 2. And third one is this sigma 2 and sigma 3. So these are the Mohr circles I am drawing. 3 more circles you can draw. Okay. Now if I draw 3 more circles, what are the maximum shear stress? So you are going to look which Mohr circle has the biggest diameter, biggest radius, because you know radius is the maximum shear stress. This is your maximum shear stress. So the biggest radius is when we take sigma 3 and sigma 1. So this is the biggest radius. Hence maximum shear stress would be maximum shear stress would be sigma 1 minus sigma 3 by 2, because this is sigma 1, this is sigma 3, and if you divide it by 2, that is sigma 1 minus sigma 3 by 2, and that is the radius, because this is the diameter. Now that value is 100 minus 0 divided by 2, that is 50 megapascal. So everyone is clear with it? Hello? Okay. Now the next question is, so your next question is a thin wall has mean radius 100 mm and wall thickness 5 mm and is subjected to internal pressure P. It is subjected to internal pressure P. It is given if the factor of safety is 2. If the factor of safety and yield stress in shear is what is the maximum value of P? Then maximum value. So I am giving you 1 minute. Please solve it. I just use the concept that I discussed here. What is the maximum shear stress? That is sigma 1 minus sigma 3 by 2, and you know sigma is 1 is PD by 2T, sigma 3 is 0. So what I would write it like here. Just I discussed earlier, maximum shear stress is minus 0 divided by 2, that is PD by 4T, and it is given your yield stress in shear is 100 megapascal, and also your factor of safety is 2. So factor of safety is called the sigma what we called, it is called maximum uh, stress upon allowable stress. So the maximum stress, suppose factor of safety is 2, it is given. So your maximum stress would be your material for which the material would fail, that is 100 megapascal. So this is the maximum stress, and your allowable stress is the stress beyond which you don't want to go. Okay, to maintain the factor of safety of 2, this is your zebra line. So this is your maximum stress, because if you go in this, the car is coming, they are not allowed to go in zebra line when the light is red. But here they make two parallel white strips. Why? This is your allowable range. You can go up to here, but here not here. So this is same with the maximum stress and allowable stress. This is the line that would lead to failure. Okay, but this is the line for the warning. So this is the allowable stress is like that. Allowable stress is I want to stop you, or shear, in terms of shear we write it as tau allowable. So your tau allowable is 50 megapascal. So I don't want to go above 50 megapascal, although I can go up to 100, but this would lead to machine failure. So I would like to go only up to 50 megapascal. That is the meaning of the allowable, and that is the meaning of maximum shear stress. That is maximum shear stress is given, and also that value is 50 megapascal. So we can solve and we can obtain the value of P. So it is given 50 megapascal. Your pressure is we need to find. Your diameter is given. Diameter is 100. Sorry, radius is 100 mm. So I am putting a diameter 200 mm. Divided by 4 into thickness T 5. So 5 for the 20. Here it is 10. So P is 5 megapascal. Is it clear to everyone? So where are the rest of one? Okay. So I am going with the thin sphere now. So this is your thin sphere. Just like you see that at this surface, the shaded surface that I am talking about, there is a stress because here the material is there and they would resist the internal pressure. Okay, what is the meaning of that? The material at this point would resist the failure. So here the longitudinal stress and compressive stress are same. Sorry, longitudinal and circumferential stress are same. Why they are same? Because sphere is in symmetry. If you break like this or if you break like this, it would be same. So they are same. That means sigma longitudinal equal to sigma compressive is equal to PD by 4T. This is your only equation in this. So corresponding the change in diameter to the original diameter, that is diametrical strain, would be, because they are same, you can write it like this. Uh, they are not only the PD by 4T. This is minus PD by 4TE into mu, and if you put it like this, it is PD by 4TE 1 minus mu. Now if I take log both sides, that would be log pi by 6 plus 3 log d, and if I differentiated both sides, that is the volumetric strain is equal to 3 times delta d by d, that is equal to 3 into PD by 4TE 1 minus mu for the volumetric strain in sphere. This is for sphere. So anyone has any problem in the derivation? I want to just emphasize you how I got PD by 40. So that's what I want to just go with it. So in earlier case, just like I said, suppose internal pressure P is acting, so P would act in the we can say that the projected area. And what is the projected area of a sphere? If you put a sphere, suppose if you put a sphere and you put below pi by 4 d square, and this is equal to your sigma, that is the stress, into pi d into T. So this is your stresses originates and leads to the force along this circumference. So inside circumference is pi d. If you multiply it by T, this would be the area of the sphere. So I hope everyone is good. Now I am going to give you some question. First, I want to take a look if I missed something or not. So a question is, okay, I am going to combine the combined question for sphere and cylinder. Suppose a question is given. It is given question. I am going to write it. A cylindrical cell or a cylindrical cell having hemispherical shell at both ends. Is subjected to internal pressure 50 megapascal if hoop strain remain constant at the junction then ratio of thickness of thin cylinder to the thickness of hemispherical ends. Your E value is 200 gigapascal and your mu value is 0.3. So I am giving you 1 minute, please look at it, then I will explain. So let me give you a diagram how the things are like. Suppose this is your cylinder. Okay, now at this end we have a hemispherical ends, that is like a cup. You can see it in many places. So it is given that internal a fluid is filled and its pressure is 50 megapascal, and it is given that the hoop strain remain constant at junction. Suppose this is a junction of your sphere and a cylinder, so hoop strain is constant at this junction. Then it is asked the thickness of the hemisphere, thickness of thin cylinder to the thickness of hemispherical ends. Now, first of all, the hoop strain will try to increase the diameter. That means, in order to the amount of which this cylinder is elongating, this sphere need to elongate that much so that they remain in contact. Okay, that means hoop strain of cylinder is equal to hoop strain of sphere. But sphere has only one type of strain, and that is we call it hoop or longitudinal. But in cylinder it is PD by 4TE 1 minus mu. Now if you just cancel every term, sorry, T1, T2, if there is a T1 and T2, they both are different. So here only this term, so I will cancel every other term other than T. So here the value is 2 minus 1 minus mu by T2. So we need to find T1 by T2. T1 by T2 is equal to 1 minus mu by 2 minus mu. So 1 minus mu is 0.7 and 2 minus mu is 1.7. So what would be the value? So I just reciprocate it. Oh, sorry. That's what I am saying. It is coming not. So value is T1 by T2 is 2 minus mu upon 1 plus mu, 1 minus mu. This is 1.7, this is 0.7, and your value is 2.48. So this is for the combined cases of sphere with the thin cylinders. Okay, now I am going to give you one more question. Okay, one more question. Anyone has any problem in this question? Hello, is it okay? Hello. So I am giving you one more question related to this topic of spherical of sphere. So it is given a spherical cell a spherical cell 1 mm in diameter and 8 mm a pressure of under a pressure of 10 bar, and you need to find the change in volume of sphere. Okay, you have given mu is as 0.25 and your E is given 200 giganewton per meter square. So your change in volume is equal to 184 centimeter cube. So I am going to give 1 minute, please solve it. How we solve this? Let me give you. So the volumetric strain sphere is, as you all know, Pd by 4Te 1 minus mu. It is coming down. This is your volumetric strain. So if you write what the value that are given are, your pressure is uh, your pressure is given around 10 bar. So it is, sorry, 1 meter, that is 1000 mm, divided by 4 into thickness, that is 8 mm, into E it is given 200 giganewton, and pressure is given in bar. So better to convert in megapascal. So it is 1 megapascal. 10 bar is 1 megapascal. You can write it at like 10 to the power 6. So it is 1 megapascal, and we are going to convert it also in megapascal, 10 to the power 3. So these are the values, and then 1 minus 0.25. This is your volumetric strain. Okay, now your volumetric strain is delta V by V, and this is the value, that is 1000 divided by 32 into 200 into 10. You know volume of sphere is 4 by 3 pi r cube. Now multiply this denominator with that RHS. It will be V into 1000 into 0.75 upon 32 into 200, 184 uh, centimeter cube. It is given in centimeter cube. 184 centimeter cube. Okay, this is your for thin cylinders. Now any question with the today lecture that I taught you with the energy methods, thin cylinders? Any question? Hello. And also with that you can say thin spheres, thin cylinders, and torsion. Today we discuss three things: energy methods, pressure vessels, and that point. So I am looking for some previous year gate question. Okay, let me see that in 1 minute. Just give me 1 minute. I am coming. uh, so I'm going with a question on uh, energy stored in so I'm going with the energy methods, and here I'm going to discuss a question. So suppose I by the energy methods, uh, we need to find the total strain energy stored in the beam. Total strain energy, as we all know, it is a bending problem, so you are going to use the equation m square dx upon 2ei. So first of all, we need to find the moment, means what is the bending moment. First of all, what is the reactions Ra and Rb? That is, Ra is equal to Rb is equal to W by 2. Okay, now I am going to write that, just couple of, now I am going to write the moment at this point A, B and C. We have two portions, so we are going to reduce strain energy as from A to B m square dx upon 2ei plus integration B to C. And at this point we have only W by 2 into x, and at this point we have this load also, so we are going to distribute it like this. So 0 to L by 2. Okay, uh, you can write it like W by 2 into x whole square dx upon 2ei plus integral L by m is equal to W by 2 into L by 2 plus x minus Wx. This is like this. So I am going to write it like W by 2 L by 2 plus x minus Wx whole square dx upon 2ei. So this is one method of solving this problem, and you can obtain the relation and the value that is come W square L cube upon 96ei. But you can also solve by the method that is, let me give you. Uh, before that we apply the theorem that is called Castigliano at this point. Now if you integrate both sides, okay, or just integrate it, sorry, yes, it is. So or we can integrate it like in other way, like write it like del u is equal to del p into delta. Now integrate, you get the strain energy delta u is equal to p into delta, and this is multiplied by half, because just like we said in the strain energy, stress is directly proportional to strain, so area under the curve is half p into delta. Okay, now you know the load applied at the center is W, and corresponding to that W location, what is the maximum deformation? I hope you all remember, that is WL cube upon 48 Ti. Okay, so I am going to write it like WL cube upon 48 Ti. So your value that is coming is W square L cube upon 96 Ei. So this is the strain energy stored in the beam. So that's why I given this question, because you can directly solve at what is the location of W, and at that location what is the deflection. So you can directly go with the half P into delta. Okay, this is the strain energy stored in the body. So I hope this is over for today, and in next class we are going to discuss the remaining topics. Okay. So anyone has any doubt, they can ask me.